Hello everyone and welcome to this lecture. In this lecture, we will talk about two very interesting, very beautiful topics in linear algebra and matrix theory. The topics is about the eigenvalues and eigenvectors. There are many applications of it. In fact, when we say about the applications of linear algebra or matrix theory, indirectly we are saying about the applications of eigenvectors and eigenvalues. These two terms were coined somewhere in 18th century when the study of rotational motion of celestial body or rigid body was going on, and few very famous names associated with this are Cauchy, Euler, Lagrange and Hilbert. So let us see what eigenvalues and eigenvectors are. Okay, by the way, there is a disclaimer. Whenever I ask some student about the eigenvalues, what are the eigenvalues, the usual answer is this. The answer is, oh, they are the roots of the characteristic polynomial of a given matrix. And I feel that this is very counterintuitive way of describing or basically introducing the eigenvalues. In fact, the introduction of eigenvalues and eigenvector is extremely simple. In fact, if you just know the matrix product, when we multiply a matrix with an vector, what happens? If you know this, you know what eigenvectors are. Okay, so let us start with the journey of introducing eigenvectors and eigenvalue. Okay, so suppose we have a square matrix of order n cross n. Okay, what happens when we multiply this matrix with a vector? So suppose I take a vector, column vector. What will be the output? The output will be another vector. Okay? Suppose I call it y, which the size of this will be same as the size of x. Okay, and you keep on multiplying different x, you will be keep on getting different y's. So what are eigenvectors? Eigenvectors are those spatial vectors such that when you are multiplying that vector with matrix A, the output is scaling of the input vector. Scaling of the, and there is one more thing to it. This input vector has to be non-zero. By the way, if you multiply a zero vector with A, right, the output will be zero. There is nothing much interesting. So eigenvectors are those non-zero vectors such that when you multiply those vector with your input matrix, the output is scaling of these vectors. So something like some scaling, suppose I call it lambda times x. When y is some lambda times x, okay, then x is known as an eigenvector. So this is an eigenvector. Very simple definition. Okay, so eigenvector and eigenvalue. So lambda is the corresponding scaling factor we call eigenvalue, and x we will call in that the eigenvector. By the way, x is here non-zero vector, so this has to be non-zero. In case zero, there is nothing interesting. So in the definition of eigenvectors, so we will take the non-zero vectors. Okay, so non-zero vectors such that the output is scaling of input vector. So let us take some examples. Okay, so this is very simple definition of eigenvectors and eigenvalues. Okay, let us take some example. So let us take very simple matrix. The matrix is suppose this. Very simple. Okay, so let us try to find some of its eigenvectors. Okay, so let us choose one vector and check whether this is an eigenvector or not. Okay, so let me just take 1, 2. Very simple one. What will be the output? The output will be yes, this will be nothing but 2, 1. Yes, 2, 1, right? Okay. Is it an eigenvector? Is 1, 2 an eigenvector? Okay, this will be an eigenvector only when there exists some lambda such that this I can write, right? This I can write. But is it possible? Is it possible? It is not possible, right? For any lambda, this is not possible. So that means 1, 2 is not an eigenvector. Not an eigenvector. Okay, so what could be the eigenvector? So let us multiply with some other vector. let us try our luck here. So 0, 1, 1, 0. Okay, let us this time try with this vector. What will be the output? Oh, the output will be 1, 1, right? But 1, 1 is an scaling factor. I mean, this is just an scaling of 1, 1, right? So you just multiply with 1. The output will be what? This 1, 1, right? So this is an eigenvector. This is an eigenvector. Okay, and the corresponding eigenvalue is 1. Very, very simple, right? And by the way, before moving to some other eigenvalue, let us see one observation. Okay, 1, 1 is an eigenvector. What about 2, 2? You see that 2, 2 is also an eigenvector. In fact, if you do any scaling of this, so basically any scaling, so suppose, so this is an also eigenvector, okay, also an eigenvector for any C, for any scalar C. Okay, but why this happens, you just check it why this happens. This is actually coming from the definition. See, whenever, so the definition of eigenvector and eigenvalue is this, right? Ax is equal to lambda x, right? Now if you replace x with some scaling of x, right? So suppose if you replace x with this some scaling of x, the output is nothing but lambda times that scaling of x. Okay, so Cx is also an eigenvector. In fact, corresponding to an eigenvalue, there can be infinitely many eigenvectors. We just keep on scaling it. Very, very good. Very good. Now let us see what could be other eigenvalue of this matrix. So 1 we have already found, right? The 1 is an eigenvalue. What could be the other eigenvalue? So let us see. So this is 1, 1, 0. Okay, let us this time see this vector 1 and minus 1. What will be the output? The output will be minus 1 and 1, and in fact again I can write this vector as minus 1 times 1 and minus 1. If you see that this input and this is output, the output is nothing but some scaling of the input. The scaling here is this. So minus 1 is also an eigenvalue, okay, and the corresponding eigenvector, one of the corresponding eigenvector is 1 and minus 1, and any scaling of 1 and minus 1 is still an eigenvector corresponding to this. By the way, now at this point I must ask you, suppose I gave you an n cross n matrix, square matrix, right? How many eigenvalues will be there? I see that corresponding even one eigenvalue, there can be infinitely many eigenvectors. So in total there are many eigenvectors. Okay, but what about the eigenvalues? How many eigenvalues will be there? Okay, we will shortly see this question. Okay, and meanwhile you keep on thinking. Okay, now let us take another example. Okay, another, in fact, much more simpler example. So what is the simplest kind of matrix we have seen? Simplest kind of matrix is just identity matrix. Let us see the eigenvectors and eigenvalues of this. Okay, what are the eigenvectors of this matrix? Okay, in fact, if you see that if you multiply any vector with this matrix, the output is the same vector, right? So if you do this, the output is nothing but, so every vector. Okay, but we have to careful here. So we have to take non-zero vectors, right? So every non-zero vector in 2D space is an eigenvector of identity matrix. Similarly, if you talk about n cross n matrix, you take any non-zero eigenvector of that much dimension, this is an eigenvector. And what about the eigenvalue? Eigenvalue here is nothing but 1, right? Because the scaling factor is just 1. Okay, so very simple one. Okay, so and now let us ask another question. Does every matrix has eigenvalues and eigenvectors? Okay, in particular let us see this matrix. One, maybe I cook this matrix. So suppose this one. Let us try to find its eigenvectors. Suppose x1 and x2. So So basically this vector, so this is x, this is suppose my a, right, is an eigenvector of a. Okay, so that means there actually is some lambda such that this equals to this. Okay, and let us solve this. So this gives you what? This gives us, I think, -2. This is x1. Okay, this is lambda x1 x2. This gives us further, yeah, so this gives the equation lambda times x1 is nothing but -x2, lambda times x2 is nothing but x1. So if I replace this x1 with here, so I will be getting this, right? So I will be getting yeah, so lambda times lambda x, so basically lambda square x2 is -x2. Okay, now remember this eigenvector has to be non-zero, right? So at least one of the entries among x1 and x2 has to be non-zero. Okay, but if I do here, if suppose x2 is 0, that will imply x1 is also 0, that means the vector is 0. So x2 I cannot take 0, so x2 is some non-zero, so I can actually cancel out this. So that implies lambda square is equal to -1. So this gives what? This gives lambda equal to some imaginary number, in fact plus minus iota imaginary number. Okay, so it may not be possible that for every matrix you are getting real eigenvalues. Okay, real eigenvalues. In fact, if you see carefully this matrix, if you take the physical significance of this matrix, suppose this one 0, -1, 1, 0. This is a matrix which rotates every vector by 90 degree. So suppose if you take, so suppose this 0, 1 vector, 0, 1 vector, right? So 0, 1 vector is, so suppose if you let me plot this vector. So 0, 1 vector is this one, right? So this is 0, 1 coordinate, right? So this matrix will rotate it by 90 degree in anti-clockwise direction. So the output here will be what? So the output will be nothing but -1, and then this will be 0. Okay, so this is very now, so basically this, yeah, -1. So in fact you take any input vector, this matrix will rotate this vector by 90 degree in real sense, right? So that means if you talk about the real axis or real numbers, there is no real eigenvector for this matrix, right? Because it rotates, right? And we have seen by the definition what it scales. Basically the eigenvectors are the vectors such that these are basically when you multiply some input vector with the matrix, right? The output is some scaling of this, right? And scaling means the direction is we are keeping same, but here the direction is changed because of rotation. Okay, very good. Of course there can be imaginary eigenvalues and imaginary eigenvectors. Very good. Okay, so before moving ahead, so let me give you some pictorial way of describing eigenvectors. So basically this, so eigenvectors are something, so suppose a vector is, suppose this is a vector and there is a given matrix A, so this vector will be eigenvector. If you multiply this matrix with this vector, the output is some scaling of this, Scaling need not to be that it has to be bigger one, it could be shrinking, elongating, or maybe 0, right? Maybe the eigenvalues may be 0 also. Okay, very good. So now the next question is how to find these beautiful numbers and beautiful vectors. Okay, so numbers are eigenvalues, vectors are eigenvectors. Okay, so how to find? So let us again go back to the definition of eigenvectors and eigenvalues. So very simple one. So this is the definition, and X here is non-zero vector. Okay, so let us play around with this equation. Okay, so I can actually write this as this, right? Ax minus lambda x, this is giving you a zero vector. Remember, this 0 is not a number, this is a vector, right? Zero vector. So I can write this further as this: a minus lambda I times x equal to 0. What does this implies? Remember, x here is a non-zero vector. Okay, what does this imply? This implies that remember, we have seen this earlier also. This is nothing but some linear combination. Okay, some linear combination of the columns of A. So suppose these columns of A minus lambda i's are this. Okay, so suppose these are the columns. The first column, second column, okay, second column, and this is suppose nth column. Okay, so this is nothing but some linear combination of this, right? Now x here is, now I mean the linear combination, what are the scaling what are the coefficients in that linear combination? The scaling is nothing but this, x1, x2 and xn, right? Xn, so basically this x I am writing it here, x1, x2, xn, so this is nothing but 0. There, that means this x1 times c1 plus x2 times c2 and so on, xn times cn is actually 0. That means that, and these all, by the way, these all xi's are not 0, right? Because this is a non-zero vector. This means what? These columns are linearly dependent. These columns are linearly dependent, and this implies that this matrix has determinant 0. This implies the determinant of A minus lambda I is 0. You can see this otherwise also. So suppose, had it been, suppose the determinant of A minus lambda I is not 0. So I am giving you now another proof why determinant of A minus lambda I has to be 0. So suppose you assume that this is not 0. In that way, what will happen? You can actually multiply by the inverse of this matrix on both hand side, but then right hand side will be 0. This will give you that x is 0, but x is your eigenvector. It cannot be 0. So this will be a contradiction. Okay, so very good. So we have seen that this implies the definition of eigenvectors and eigenvalues giving that determinant of A minus lambda I is 0. Okay, now this gives us a polynomial. When you solve the determinant of this will give you polynomial, and roots of these polynomials are nothing but the eigenvalues, these lambdas. Okay, very so now you can answer how many eigenvalues will be there. This polynomial is of degree n, right? If you are solving this determinant, you will getting the polynomial of degree n, so there will be n roots of eigenvalues, and corresponding to every root there will be many, in fact infinitely many eigenvectors. Okay, very good. So you can now I mean this is your DIY, so you can now find the eigenvalues and eigenvectors of the matrices that we have seen as an example. Okay, just practice, just you calculate using the determinant. Now we will see the properties of eigenvectors depending upon the nature of the eigenvalues. Okay, and we will see many applications of this framework. So if the eigenvectors are coming out to be very good, these are the corresponding matrix is highly useful for us. Okay, very good. So let us start with some nice properties of eigenvectors depending upon the eigenvalues. Okay, so the first result is this. So let me write this result as a theorem. Okay, the theorem is the eigenvectors corresponding to distinct eigenvalues are always linear independent, and we will see that whenever the eigenvectors are linearly independent, in fact we can see much more whenever the eigenvectors are orthogonal, lives become super easy for us. Okay, so this theorem is about when the eigenvector when some eigenvalues are distinct. Okay, so the theorem is this: the eigenvectors corresponding to distinct eigenvalues are independent, linearly independent rather. Okay, so very good. So are linearly independent. Very easy to prove, very easy to prove, but very useful fact. Okay, very good. Okay, so suppose lambda 1 by default lambda 1 lambda 2 up to suppose lambda t are the distinct eigenvalues, suppose are the distinct eigenvalues. Remember, the eigenvalues can be repeated. When we, the very typical example is your identity matrix, right? All the eigenvalues are equal to 1. So 1 is repeating n times, right? Okay, very good. And the corresponding, let us take some corresponding eigenvector and let us take some corresponding eigenvectors as v1 v2 up to vt. Okay, so we have to prove that v1 v2 up to vt, all these are forming a linearly independent set. So let us assume that they are not linearly independent. They are forming a linear. So we will prove it by contradiction. Okay, so but we can assume one thing. Okay, but up to some vectors these are linearly independent. Okay, so suppose without loss of generality, so let me write it this. Okay, assume that maximally up to j vectors are forming a linearly independent set, and that means any set of j plus 1 vector is forming a dependent set. And without loss of generality, we can, let's suppose v1 v2 up to vj are actually forming a linear independent set, are forming a linearly independent set, where j could be maybe greater or equal to 1, it could be 1 also, and less or equal to t. Okay, but if you take any j plus 1 vectors, they are forming a dependent set. So suppose, so that means what? But vj plus 1 you take this vector. By the way, this ordering doesn't matter, you can take any j vectors, those which were actually forming a linearly independent set. Okay, and you take some extra vector j plus 1, this you can write as a linear combination of these vectors, because we are assuming that they are forming a dependent set. Okay, they are forming a dependent set. Very good. So this can be written as linear combination of this, basically ci times vi, where I equal to 1 to j. Okay, very simple. Now let us multiply this with, suppose the matrix was A. Okay, A n cross n matrix. Okay, so if you do this, suppose this matrix was A, so aj vj 1 plus, so you can actually write this as, right, so summation 1 to j. Very good. A ci vi, right, very good. Now if you see, so this quantity will be what? Because they are due to the definition of eigenvector and eigenvalue, this will be nothing but lambda j plus 1 times v j plus 1 equal to this, right? So this we can write as summation I equal to 1 to j, okay, lambda I ci vi. Very simple, very simple. Okay, now you see that now this quantity you can actually write from here, right? So vj plus 1 is nothing but this, so vj plus 1, so lambda j plus 1, let me write it first, times this is nothing but summation I equal to 1 to j, very good, ci vi, and this is equal to this, I equal to 1 j lambda I ci vi. Okay, now just rearrange the terms, so you will get this you will get I equal to 1 to j lambda j plus 1 minus lambda I times, now you do ci vi equals to, so this implies equals to 0, right? Now you see that for any I, lambda is not equal to lambda j plus 1 because these are distinct eigenvalues. Okay, so this implies what? This implies that Ci, and moreover all the Vi's, right? V1, in fact, so not implies is said. So we have already seen that V1, V2 up to Vj are linearly independent. So this implies what? This implies that all Ci's are zeros. All Ci's are zeros. This is not Ci's are 0. Okay, but what if Ci's are 0, but we have written this Vj plus 1 as a linear combination of all Vi's, but if Ci's are 0, this implies that this is 0. Vj plus 1 is 0, but this is an eigenvector. This cannot be 0. So this is a contradiction. Hence your theorem is true. Okay, so basically, so all this, hence the theorem is true. So let me just write this. Hence the theorem is true. Hence the result follows. Okay, implies that x j, okay, Vj plus 1, sorry, Vj plus 1 is 0, a contradiction. Very, very good. Okay, very, very simple. Now let us see another result. Whenever the matrix is symmetric and suppose the eigenvalues are distinct, we can say in fact much more than just linear independence. This time we can say about the orthogonality. Okay, so the next result is this. Okay, suppose the matrix, let A be a symmetric matrix, okay, then the eigenvectors corresponding to two distinct eigenvalues are orthogonal. Okay, very, very good. So very, very simple proof. Okay, so suppose two distinct eigenvalues are alpha and beta. Okay, and corresponding eigenvector are, suppose you take v1 and v2 respectively. So v1 is just alpha times, or maybe lambda 1 and lambda 2, you just take these eigenvalues. Okay, so v1 and v2 equal lambda 2 v2, and it is given that lambda 1 is not equal to lambda 2. Very good. Now you see that very, very easy to see. Okay, so we can actually multiply the first equation by the transpose of v2. So basically v2 transpose a v1. So this will give you lambda 1 v2 this. Okay, and similarly if you see we can actually multiply this quantity with the transpose of v1 on both and side left towards left. Okay, so v1 transpose a v2 lambda 2 v1 v2. Okay, now what next we can do? And by the way, if you take transpose of this, these are just numbers, by the way, these are just numbers, so the transpose will be same. So if you just do this, this implies this, right? So v1 transpose, then A transpose, but A transpose equal to A, right? A transpose is equal to A because the matrix is symmetric. So this is equal to v2 times lambda 1 v1 transpose v2. Now what we can do, suppose this is 1, this is 2, now just subtract and the result is in front of you. If you subtract this, this will give, so that this quantity will be 0, so 0 equal to lambda 1 minus lambda 2, okay, times v1 transpose v2, okay, but we know that these two lambda 1 is not equal to lambda 2, that means this is non-zero, so that implies v1 transpose v2 equal to 0. Hence these two vectors are orthogonal vectors. And by the way, now you must be asking why you have asked only about two distinct eigenvalues. Suppose there are k distinct eigenvalues. What about the eigenvectors? What about the corresponding eigenvectors? We will see that in next theorem. We will see in the maybe next lecture onwards, that you can always cook irrespective of whether the eigenvalues are distinct or not. Okay, you can always come up with n orthogonal eigenvector corresponding to the eigenvalues of a symmetric matrix, and that is why this the symmetric matrix becomes one of the most beautiful matrix and most applicable matrix for different purpose. Okay, so this is just a beginning. Okay, very good. Now, by the way, what could be the relation of eigenvalues with the fundamental quantity in matrix? The fundamental quantity that we have seen till now is what? The determinant. What could be the relation of eigenvalues with the determinant, or in fact what could be the relation of eigenvalues with the determinant of the submatrices of the given matrix? Okay, so I am writing the next theorem, but this will be a DIY for you. You just think about it. Okay, just proving it. This is a very beautiful theorem. Again, a very nice applications of it. In fact, we can just see one applications of the theorem that I will write to find the number of spanning trees. The number of spanning trees just using the eigenvalues. Okay, so let me now write the statement. The statement is this. Theorem. Okay, have some patience because this could be slightly lengthier one. Okay, let A be an n cross n matrix and n cross n matrix. Okay, so there will be n eigenvalues, right? B, the sum of product of eigenvalues taken k at a time equals to the sum of principal minors of A. Okay, what are the principal minors? Okay, firstly let us see what are the principal minors, and then we will see what we mean by taken k at a time. Okay, principal minors are nothing but this. Suppose A is this matrix of order n cross n. Okay, you choose, so suppose S is some subset of numbers from 1 to n. Okay, you choose some S is some subset, you choose rows corresponding to S and also the columns corresponding to S. Okay, so the submatrix formed by those rows and columns is a principal submatrix. Okay, so that we will denote it by maybe this A, maybe you can denote it by this, right? So we have actually seen this notation, so S. Okay, so this is a principal submatrix. Okay, and the determinant of this is minor of A, and suppose the size of this is, suppose if size is k. Okay, so this is minor of A of a minor of size k. Okay, of size k. In this way, there can be equals to sum of principal minor of A of size k, or order k. Okay, whatever name you take. Okay, very good. So it said that if you take the eigenvalues k at a time, product them and do all combination of k such eigenvalues and product them and then take the sum, this will be equals to the sum of determinants of principal sum matrix of size k cross k. Okay, so these are called actually minors. Okay, so you have to prove this result. Okay, so thank you very much. I hope you have enjoyed the introduction of eigenvectors and eigenvalues and some properties of it. So we will see many of them. Okay, so thank you very much and see you in the next lecture.